the final talk before lunch. So this is by Changxin Ding, and it's on Lorentz polytopes and some invariants of a graph.
Okay, thanks for having me. I guess you can hear me, right? Okay, great. So, uh, this is some work in preparation. I'm writing the paper, although in some sense, 1 year ago it was in preparation, but now still in preparation. So if you saw me in Bochum in the FIPSEC meeting 1 month ago, so it's also on Lorentz polytope, but this work is different from that. In some sense, in logic, they are completely different. That's what I find amazing with the Lorentz polytope. It can really explain many different things. So let's go. Here is just a brief overview. So basically, I want to study the H vector of a regular matroid M, which is a combinatorial object. Then I want to study that in a geometric way, meaning I try to make use of the Lorentz polytope of this regular matroid M, and I try to study the H star vector of it. So this is about the discrete geometry. So some more key words in my talk will be passivity, which basically is the complement of activity. If you have learned the classical activity theory concerning the third polynomial, then sharing, which is a classical geometric thing, and the reduced divisors of a graph. So let's see. I need to define the pure simplicial complex. So basically, I start with a ground set E. Then I start with some subsets of this E. The only requirement here is that they have the same cardinality. Then we can get a pure abstract simplicial complex by just taking all the subsets of it and then take the union. Then these elements in this simplicial complex is called faces. For example, you can consider you start with a matroid, then you take all the independent sets. Then these things will just be bases. Since I'm studying graphs, so I'm using the letters T. Okay, there are actually two versions of pure simplicial complex. One is abstract, which I just defined. The other is a geometric one. I think the term pure geometric simplicial complex is too long. So instead, I will use the word triangulation instead. Basically, they mean the same thing, and this word is very, It's very intuitive. So let's see. So for a triangulation like this, you can define a pure abstract simplicial complex in the obvious way. So here T1 is you look at this face is just 1, 2, 4. T2 is just this 1, 1, 3, 4, and T3 is 2, 3, 4. Then you take all the subsets, you will get a simplicial complex. We can actually do that in the other direction. If I start with a pure abstract simplicial complex, I can construct a geometry one by doing so. So first you look at the ground set E. Then for each element in this E, you construct a basis in the vector space Rn. Then if you look at this face 1, 2, 4, you just take the convex hull of the corresponding vectors. So you sort of can recover this picture, but it is in a higher dimensional space. So I will call it a realization of this simplicial complex. There could be other geometric realizations, and this is just some canonical one. Okay, so some sense I want to emphasize that this is a geometric object instead of an abstract one. So I will denote this face by simplex of T1. So it's just some intuitive notation. Okay, to define H vectors, I need to introduce something I call half-open simplex. Okay, so let's see. So here is just a simplex, which is a convex hull of these vectors. So then I want to remove the face here. So in this talk, facet will mean codimension one face. So I pick up a vertex here. Then algebraically, so I will add one more condition. So this is V1. So I hope the coefficient on V1 is strictly positive. So geometrically, I will remove this facet. So I call the whole thing a half-open simplex. So basically, a half-open simplex is a simplex. Then you remove some facets. Here is an example where I remove two facets. So I pick V1 and pick V3. I remove this facet and remove this facet. So algebraically, it's just add the two conditions here, x1 and x3. The coefficients must be positive. So now I will call these elements here passive elements. Then you will see why. So, okay. Then this is about the passivity decomposition of a pure simplicial complex. So geometrically, so I identify this thing with a triangulation. Then I can partition the whole triangulation into disjoint half-open simplexes like this. So this is a triangulation. I can take the union of these things, but if I want to do disjoint union, so I need to remove some facets here like this. So this gives me a passivity decomposition. Okay. Certainly, I mean, if you look at this half-open simplex, then this vertex will be passive with respect to this decomposition. If you are familiar with the abstract setting, so you should recognize this. So this is they are sort of equivalent, but you haven't heard of this, then you just take this as a definition. So here I decompose this set into disjoint union of these intervals. I mean, the interval simply means all the subsets between A and B. So here I call here this set is actually the set of passive elements I have just defined. So in this concrete example here, T1 has no passive elements, so this is the empty set. For T2, then this element is passive, so it's just 3. So for this tree, I have two passive elements, 2 and 3. Okay. So a way to get a passivity decomposition is to make use of sharing. So a sharing of a triangulation or a simplicial complex is a linear order of these maximum simplexes, such that each time you need to attach these simplexes one by one. So each time when you consider the new geometric objects we have, it means you take one, then you need to minus all the union of these things. If you get a half-open simplex, then this will be a sharing. Here I will give you a non-example. If you look at this thing, if you do T1 first, then you do T2, then the problem here is the new part is T2 minus this one vertex, but this vertex is not a facet, it's not codimension 1. So this will not be a sharing. So if you want to have a sharing, you must do this first, then this and this, something like that. So let me see. Clearly, any sharing will give me a passivity decomposition. Now it's a good time to define the H vector. Basically, it's a sequence of numbers. So given a passivity decomposition, you just hk, so you fix a number k, like k is equal to 2. Then you count the number of these ti such that the number of passive elements for this ti is exactly 2. Then you count how many of them. So let's see one example. So this is a triangulation. So here, first I count these trees with no passive elements. There's only one, so this is 1. Then you look at the T2 and the T4. They both have exactly one passive element, so H1 is 2. Then for T3, it has 2 passive elements, so H2 is 1. So for H3, H4, they are all zeros because it's not relevant. So the point here is H vector does not depend on the choice of this decomposition. So that's why I call it an invariant. That's the point. So now we move to matroid. So let's see. So I start with a matroid, then I take all the bases. Then I will get a simplicial complex. If I order these elements in the natural way, it's like 1 is less than 2, blah, blah. Then I can define a lexicographic order on these maximum simplexes or these bases. So which means if you have two bases, you first compare the smallest element, now they are equal, then you see the next one, 3 is smaller than 4, then the conclusion is this set is smaller than this set. So 8 and 9 and 5, 6 are irrelevant here because 3 is already less than 4. Then this order will always give me a sharing of this simplicial complex. Then hence I can get a H vector denoted by H of M. Here is just a remark of if you are familiar with the classical activity theory. So if I use this order to define the passivity, then for each base, so an element is passive if and only if this is not the minimum one in the fundamental code circuit. So you take the complement, you will get the familiar notion. E is active if and only if it's the minimum one in the fundamental code circuit. So this is in general, it's a more general notion. It generalizes the classical activity theory. Okay, so this is a Matroid workshop. So let me introduce something new in case you don't know that. So there are actually two relevant cryptomorphisms here. So we can define a Matroid in terms of simplicial complexes. So I have two. So the first one is I start with a pure simplicial complex. If any linear ordering on E makes a sharing by making use of this technique, if you can do so, then this simplicial complex will be a Matroid. The other one is we can define matroids just by talking about the purity. So basically, you start with a pure simplicial complex. Certainly, it's not necessarily a matroid, but if every restriction is still pure, then it will be a matroid. By restriction, you can think of just the restriction of a matroid means the deletion. You just delete, you pick a subset, then you restrict everything to that set. Okay, here. Okay, now I can introduce this conjecture. Stanley has a conjecture which is sort of a long conjecture. I mean, it was a long time ago. So the conjecture is the H vector of any matroid is a pure O sequence. Then what is a pure O sequence? So you start with monomials of the same degree. That's why it's called pure, like this. Then you go down, meaning you take all the factors of these monomials. Then you will get a poset. Then you count layer by layer. For this layer, I have only one element. For this layer, I have 3 elements. For this layer, I have 4. So I get this vector called a pure O sequence is 1, 3, 4, 0, 0, 0. Then the conjecture here says you can. So any H vector of any the H vector of any matroid should be a pure O sequence, meaning you should be able to find such monomials. Okay, let's see some progress. The good news is we know in some cases this conjecture is true. The most relevant one, I mean, to my talk is Marino's result. So he proved that it holds for cographic matroids. And actually he, with some collaborators, they proved that it holds for paving matroid. These are good news. And there are some other works like prove in some sense, some low rank, something like that. There are a lot of them. I cannot list all of them. The bad news here is we do not even know whether it holds for graphic matroids. So let's see. Here I want to explain Marino's result a little bit. So if you search online, then you find Marino's paper. You will find his paper is in terms of recurrent sand pile configuration, or sometimes called critical configuration. I need to change the term here. Our term here is reduced device, or sometimes we call it G-parking function. You need to believe they are equivalent. They are not the same object, but they are equivalent. Now I can rephrase Marino's result in this way. He first proves that all the reduced devices of G, basically you do the statistics, you will find, you just count, you will find that this will give us the H vector of the cographic matroid. Then he proved that the reduced devices, they will give us a pure O sequence. So this proves the conjecture for the cographic case. Now you might want to ask what a reduced divisor is. This is sort of the thing I don't really want to talk about because it's sort of useful or sort of useless for you to understand the talk, but I will just go over it quickly. So we fix a graph G, then we fix a vertex Q. So a Q-reduced divisor is basically a function. So you look at this graph. Basically, I'm putting some numbers, some integers on these vertices, so it's just function. It should satisfy some conditions. So the condition is for any cut. So a cut just is a two-partition of the vertex set V. So now I write a V as Q union R. So I assume this source vertex Q is in Q. Okay, then for any cut, I should be able to find a vertex V here, V here, such that the number I put on V is smaller than the number of edges connecting V and Q. This is long, it's confusing. Let me show you one example. You look at this graph. So here's a divisor, so it's 1, 2, 0. I claim that this is not reduced. Then you need to do some exercise. So it's for any cut there exists. You take the negation, you will get there exists a cut here. This is the cut. So I want to show that if for any V this is true, that it will be reduced. But now I claim that's false. So I find a vertex 2 here. I find this vertex here. There are two edges connecting V and the other part. But this number is 2. This is not true. So this is not reduced. Then if I decrease the number, then this will be a reduced divisor. Basically, this gives you an idea. There should be only finitely many reduced divisors. So because if you go down, it's better. Okay, let me just point out the fact that reduced divisors are good because this forms a representative set of the sample group. Okay, I have about 8 minutes to go. So our plan is to use Lorentz polytope to give a new proof of Marino's result. Here I want to give a remark. I'm changing the terminologies here. Basically, we want to study the H vector of the co-graphic matroid using the passivity of this matroid. Then I need to take the dual. So instead, I will study the external activity of the graphic matroid, or just the graph. Here, by internal, I mean edges in the tree. By external, I mean edges out of the tree. Okay. Here is our main player, Lorentz polytope, defined for, actually I can define it for any regular matroid, but now I defined it for the co-graphic matroid. So I started with a totally unimodular matrix representing this co-graphic matroid. Then I put two identity matrix here, I get a large matrix. Then I have 2n columns. I have some rows here. Here, this is 2n minus the rank of the graph, meaning you take any spanning tree, you just count how many edges, then you get this number. So the Lorentz polytope is defined to be the convex of these 2n columns. Yeah. So the only thing you need to actually remember here is the Lorentz polytope has 2n vertices. So each column is a vertex of this polytope, and the dimension is here. Yeah, it's almost a 4-dimension because I only have this. I mean, you counted the number of rows. It's this number, but it's a convex hull. It should be on a hypersurface. So this is almost a 4-dimension. Okay. Then how to understand the Lorentz polytope in a combinatorial way? Here is the combinatorics. I start with a graph, then pick a vertex Q, then label the 2n vertices of P. So remember, I have 2n vertices of P. I labeled the vertices of P using 2n arcs. It's here. So here, n is the number of edges of G. I give 2 directions for each edge, so I will get 2n arcs. So now in your mind, the Lorentz polytope P is the convex hull of these arcs. So, but they are just labels. So what I will do is I consider all the spanning trees, which are in red. I consider all the spanning trees of the graph. Here I have 8 spanning trees. I orient each tree toward Q. in this way. So here is Q. I just orient each toward Q. Then I take this picture. You can see in this picture I have 1, 2, 3, 4, 5, 6, 7 arcs. 7 arcs. This will give me 7 vertices of the Lorentz polytope. Then I take the convex hull of them. I should be able to get a maximum simplex of the Lorentz polytope. This is just a fact. Then all the configurations here, I will get 8 maximum simplexes. They will form a triangulation of P. That's the point. So for every graph I do this, I orient each tree toward Q, then I will get a triangulation of this Lorentz polytope. Okay, then I have a triangulation so I can take a sharing. So I take this sharing. Okay, now the blue arcs means they are passive. They are passive. So they are passive elements. Okay, I have this thing. So it looks complicated. So first let's sort of project this picture to the sharing of the simplex associated to the co-graphic matroid here. So here for the trees, so they are in the red dotted lines. Because we are talking about the co-graphic matrix, so we needed to take the complement. So now here are the bases. So I have a sharing of this. So then you need to believe that so all the passive elements here will be sent to the passive elements here, so sort of a canonical projection here. The corollary here is they share the same H vector. Okay, then in this example, so H0 is 1 because this one has no passive elements. Then you can find 3. Picture having exactly 1 passive element, and there are 4 of them having exactly 2 passive elements. Then the question here is why do we need this thing? Because this looks simpler. That's mainly because this is complicated. It's good. So we can do something we cannot do here. So let's do something here. So we count the number of passive arcs, meaning the blue arcs, toward each vertex. Here I label each vertex by A, B, C. Okay, so let's see this picture. So I counted the number of passive arcs toward these 3 vertices, so I'll get 0, 0, 1 here. 0, 0, 1, because there are exactly 1 passive arc toward this vertex. Then let's see another example. So look at this picture. I have 2 passive arcs toward this vertex, so this will be 2. For the other 2 vertices, it will be 0. So I just get these numbers here. These numbers. Then I present these numbers in terms of monomials. So I have these labels here. So this is 0, 0, 0, meaning A to the 0, B to the 0, C to the 0. So this is 1. Then I have 1 here. So this is vertex C. So it is a monomial C. I do that for all these monomials. I will get this thing. Then the claim here is these are Q-reduced divisors. These are Q-reduced. They are exactly all the Q-reduced divisors. Then according to Marino's result, it means this will give me the pure O sequence. This is, I mean, we can only do this for this complicated picture. If for just for the simplicial complex associated to the original matrix, there's no way for us to get these monomials. Okay, the second claim is that for each tree, I will get a Q-reduced divisor, so I get a bijection here. I can do that for any passivity decomposition. I will get a different, I mean, maybe they are coincidence, but in principle, they should be different. So different bijections. In particular, I can obtain 2 known bijections defined by Corey-Lebon and Bernardi. By the way, Olivier Bernardi was my advisor, so that's why here the sharing order here actually it comes from the Bernardi bijection. I constructed this thing to recover the Bernardi bijection here. Okay. Now I have. Give me 2 more minutes. So I needed to talk about the geometric side of the thing. So it's H star vector. H star vector of a polytope comes from dilation. Basically, you dilate the polytope, then you count the number of lattice points inside that. Then you take the generating function, you will get a series. The claim here is that if a polytope has a unimodular triangulation, then H star should coincide with H. This is a classical result of Stanley. So in our settings, in our example, this Earhart series of P is just this one. You see this 1, 3, 4, 1, 3, 4, they are exactly the H vectors of these things. So, but this is not good enough because we want to have these monomials. What we will do is we sort of use a finer construction. So this is the old dilation. So for each element, we use the same scalar k. You dilate it, you get this thing. In our proof, we will use a new dilation, meaning since we want to count the number of passive arcs toward a fixed vertex, so it's like this is vertex A. So I should give these two arcs the same scalar, but for the vertex B, I should give a different one. So I have 4 different scalars, KQ, KA, KB. So if I dilate the polytope in this way, so I will get a series like this. So this looks awkward, but by a variable substitution, I will get a series like this. Then you compare that, you will see that the numerator will exactly be the sum of these monomials. That's how we find these reduced divisors in this Lorentz polytope. I guess that's a good way to stop. Thank you.
Yeah, thank you very much. So, did you have any announcements? Yeah. Okay. So since time is tight, I think we should head off to lunch. But yeah, thank you once again.